too. Absolutely the case. However, to do that requires a configuration change. That requires work.
Yeah, and you know how I feel about that.
Same way I feel about it. All right?
Should be avoided at all costs.
There you go. Okay. At this point, I'm going to go into the technical deep dive. I'm Rory Bolt. I'm the CEO and founder of Proximal Data. So, Proximal Data has a caching product called AutoCache that is a hypervisor-based read cache for accelerating I/O. In developing any caching solution, there are a number of considerations that you have to make. Okay? The first consideration is what algorithms you're going to use. And in fact, most traditional caching algorithms have been developed around RAM as the caching device. In fact, today, RAM is far and away the most prevalently used caching resource. Because of this, most traditional caching algorithms don't consider device asymmetry, right? It's pretty much constant speed whether you're reading or writing RAM. And certainly, there aren't wear-out considerations whether you're reading or writing RAM. Flash is fundamentally different. Flash is not RAM, right? It's very asymmetric. Writes are much slower than reads, and writes induce far more wear than reads do. And in fact, Flash is fundamentally a consumable resource, a consumable media, right? It does wear out. So there is a very, very real cost in terms of lost performance opportunity as well as Flash lifecycle management. There's a very, very real cost in placing data into a Flash-based cache that is never going to be read again, okay? Or not read often. The next thing to note is that hypervisors have very, very dynamic I/O patterns, right? vMotion makes I/O loads, I/O streams appear and disappear at seemingly random times as far as the storage infrastructure is concerned. And because of the fact that there are multiple guests running multiple applications and guests transitioning on and off of machines, it's very beneficial to have an adaptive algorithm that can learn the I/O patterns and adjust strategy based upon real-time feedback mechanisms. Okay? The next thing to consider is that, in fact, hypervisors are almost always shared resource environments with external shared storage. Some people do run DAS for their storage, but even in the DAS devices, there's a real cost in terms of performance if, in fact, you block one process while you're trying to determine if you can accelerate a second process. Okay, so any latencies that you introduce within a hypervisor while you're trying to determine whether or not you can accelerate an I/O have a negative effect on the other guests in that same hypervisor, right? And then the final note on there is that quotas can have very unexpected side effects. And this is something that we'll hit upon a little bit later in the presentation. But in fact, we had customers ask us, because we self-tune, we don't require the end user to dedicate cache resources to any particular virtual machine. It's all merit-based, and we will allow some virtual machines to have significantly greater cache resources than other virtual machines. And some of the early feedback is, well, is there a way I can prevent that? Can I put a quota on there to make sure that someone doesn't take up too much cache resource? And this is a very natural thing for people to inquire about, but the unintended side effect is that if, in fact, you have a guest that is so hot on its I/O processing that it's getting a sort of unfair, in quotes there, unfair amount of cache resources dedicated to it. If you put a quota on its cache resources and limited how much cache it can consume, that's not going to stop it from issuing that I/O. In fact, what you're going to do is stop satisfying all the I/O out of the cache, and you're going to push that I/O request for that guest off onto the backing store itself and have the exact opposite of the desired effect, right? By limiting the amount of cache,
if that undeserving VM is on the same backing store as the deserving VMs.
Correct. But right?
if they're on separate backing, the truth is there are applications in most data centers that demand a lot of IOPS, but whose performance, whose execution time is non-critical.
Right.
And if I put those guys on a different backing store,
right,
I would like to say, just give that guy a tiny bit of cache, because I don't care if he runs slower.
Right.
And I want to accelerate this other guy.
Right. And we do have some answers around that type of requirement. Okay. And then the final note on here is right around, as a caching strategy, provides the best performance and wear trade-off, which is to say, if in fact you look at the device characteristics, if you can avoid writing data to the flash that is not going to be read often, that is going to be the best fundamental usage of the flash. Flash is best suited for applications that read data far more often than they write that same data. Okay. So, I've mentioned we use adaptive caching. I realize that this may be something that not many people are that familiar with, so I wanted to go into a little bit of depth about the basics of adaptive caching, some of the techniques we use within our product itself. And so, for any cache, they're all at their heart a basic address mapping, address translation, indexing application where you're mapping physical locations on one device to physical locations on another device. And so you end up with these indices that point to where the data is located at. And we refer to those indices as the metadata. So within the cache, there's the actual user data itself, which is identified as the cache data at the bottom of this diagram. The next band above that is the metadata, which are the pointers to the data, along with any sort of algorithmic data that's associated with your caching strategy. And so there are some very classic caching strategies. The most recently used strategy where that metadata might be a timestamp or a linked list to order the data. There's also MFU, or most frequently used caching strategy, where that metadata may include counts of how often a piece of data has been asked for. The takeaway is, though, that there's always some metadata associated with the data within a cache, and the amount of metadata is directly proportional to the amount of cache that it's managing, right? And so in this diagram, we're illustrating two different caching algorithms, algorithm A and algorithm B. They both have proportional amounts of metadata associated with the end user cache data itself. And you can see that in this particular example, algorithm A has far less cache resources, a far smaller cache strategy than algorithm B is. Okay. Up above that, we've added the notion of ghost data. And this is how traditional adaptive caching techniques work. And you'll note that the amount of ghost data is inversely proportional to the amount of metadata, which is to say, algorithm A has a very small amount of metadata because it has a small amount of the cache that it's managing. It has a relatively large amount of ghost data. And
could you define ghost data?
Is that the working set for the?
No, it is not. I'm going to define ghost data. Ghost data is used to track entries that had previously been in the cache
And
but
flushed
have
out.
been evicted or ejected. Therefore, they are ghosts, right? They're no longer living in the cache, but they had been in the cache before. So think about it.
So metadata that points to data no longer in the cache.
And you're keeping that metadata around?
And we're keeping that metadata around because if you think about it, the combination of algorithms A's metadata and its ghost data represents a what if. What if algorithm A had access to the entire cache? How would it have performed? Okay. Likewise, algorithm B's ghost data combined with its metadata is a what if. How would algorithm B have performed if it had access to the entire cache itself? And the metadata and the ghost data is all in a common index. So you do a single lookup. You get a request for a block of data. You look it up in the indices, and you can see, is it a miss? It's never been in the cache. I know nothing about it. Is it a hit? If it was a hit, was algorithm A's hit or was it algorithm B's hit? Was it a hit in one of the ghost lists? Meaning algorithm A had identified this as cache data previously, but wasn't able to hold on to it because it didn't have enough resource. Or algorithm B had identified this as something that should have been cached, but wasn't able to hold on to it because it didn't have enough cache resource. And so it becomes a trailing edge historical feedback loop that says, based upon the trailing data, should algorithm A or algorithm B be using more of the cache? And you can dynamically adjust the division.
So if there's a high enough ghost hit rate, then you can adjust the cache space you're allocating
to the different caching strategies, right? And this is a very simple illustration of it with only two algorithms. Of course, you could have any number of algorithms that you're having in real-time competition against each other.
Right. And that ghost data is the fat part of the tail, not the long tail, right?
It had to be in cache at one time, right?
It had to have been in the cache at one time.
Yeah, but if the server's been running for a year, I don't really care about stuff that was in cache 6 months ago. I care about stuff that was in cache.
Yes, they are limited in size and duration.
All reads are cached?
We'll get to that in the very next slide. But
For the segue, right?
that is, in fact, an implementation decision for people. And so when people see this, one of the natural things to say is how much does all this metadata cost in terms of resource usage? In fact, indexing of the caches is a primary area of focus for us and something we spend a lot of time on. Our overhead to maintain these metadata structures is 1/1400th the size of the cache that we're managing, or far less than 0.1% overhead. Okay. So
More to the point is how the hashing algorithm to get into the metadata and making sure you don't have to do multiple hashes, and if you've got a ghost hash and a non-ghost hash, trying to make sure all that doesn't interfere with the actual I/O activity.
correct. You want to make sure that the processing overhead, in addition to the resource overhead, is modest. Okay? So, if you like that, let me tell you about something else that we did on top of that. So, adaptive caching is something that's known in the trade. You could look it up on Wikipedia and you'd get a primer on it, right? We actually have a patent pending on an entirely new concept called Glimmer Entries. Glimmer Entries are like ghost entries, but ghost entries refer to things that happened in the past. As you might tell from the name, Glimmer Entries are forward-looking hints. And so we actually track data that's never made it into the cache yet. And this is back to your previous question, do you cache all reads? No, we do not. The first time we see a request for data, we put it into a Glimmer entry and say, okay, someone's asked for this data. This may be interesting. This may be worth caching in the future. All right? So, once again, it's one big unified index with a single lookup. We can tell, is it in the cache associated with an existing algorithm? Is it not in the cache, but in the ghost entries for an existing algorithm? Or has it never been in the cache, but we've seen it at least once before? It's a Glimmer, right? And using the Glimmers, we're able to set policy and control how things are pulled into the cache. We can set policy around how many times we have to hit something in the Glimmer entries before we'll pull it into the cache. And we can also set policy around what sort of temporal locality or what sort of interval those axes have to be within before we'll consider something as being worthy of the cache itself. Why do we do this, okay? What's the benefit? Well, once again, if you pull something into a flash-based cache, the first time you read it and you never read it again, you've provided no benefit and you've worn the flash out, right? That's one reason why we do this. The second reason is, in most environments, there are routine maintenance tasks, virus scans, backup jobs that rumble through tremendous amounts of cold data. The Glimmer lists act as a pre-screen and prevent these routine maintenance tasks from both evicting valuable hot data as well as unnecessarily wearing out the flash itself, right? Another thing that Glimmer lists are capable of doing, because of something I sort of haven't really explained fully here, I made some mention of it previously, but we track which virtual machine instance is associated with which cache block. And since we can associate the I/O with the virtual machine that issued it, we can use the Glimmer lists to detect sequential access patterns, even though they've been interleaved with other accesses from other guests, right? So think of the hypervisor as being this giant I/O blender that's taking all these separate I/O streams, aggregating them, and presenting them down to the physical layer. We can essentially reconstitute the logical context and detect sequential accesses and potentially do altered read-ahead strategies, even though it appears to the storage system that it's truly random I/O, when in fact it's not. Another unique innovation that we've done is around pre-warming of the cache on vMotion between physical hosts. And so I'm going to be explaining how we do this and why we do it. The first thing is vMotion is always orchestrated by vCenter, and you can register in vCenter for notification on vMotion events, and we do so. So vCenter will tell us when a machine is going to be vMotioned. And we take note of the fact that a virtual machine is going to transition from host A to host B. Once we have that notification, we start the pre-warm process. And what the pre-warm process is taking all that metadata that's associated with the cache entries for that guest, that virtual machine, and bundling them together, and we transfer the metadata through the shared storage to the target machine. That metadata represents all the machine learning, all the analysis of the I/O patterns of that guest, the glimmers of what's maybe interesting in the future, the ghosts of what had been interesting in the past. All of that knowledge that's been gathered around the I/O processing of that guest is transferred, right? The other thing is, of course, the list of the blocks that were in the cache for that guest. And that list of blocks that had been cached for the guest it's rank ordered from the hottest of the hot down to the coldest of the hot. And so we transfer that metadata over to the guest, to the target, and we can begin an asynchronous background task of prefetching that data that should be in the cache for that guest, and we can prefetch it in rank order.
How do you transfer the metadata through the shared storage when you don't actually have any locations on the shared storage to do this sort of thing?
You can write a file.
Right? It's a
VMFS is a file
shared
system.
file system. It's VMFS.
No, it's a shared block storage, actually. It could be anything.
Well, if it's VMware, it's either NFS or VMFS.
In fact, you are right. And so it is done through a file in the shared file system. Okay? The background test starts pre-warming the cache
It is shared block, but that's underneath.
Yeah.
in rank order. And in fact, that's all going on while the machine is still in
Not
flight.
DAS if you're doing vMotion.
Right. Okay. Ray brings up and you support DAS.
Correct.
And now vMotion supports DAS.
Well, storage vMotion supports DAS.
Extended vMotion supports DAS now.
Right.
But you're not pre-warming in that case, right?
No.
Okay.
Okay. The final note is that once the vMotion has been accomplished, we have a mechanism that allows us to instantaneously and atomically invalidate all of the data that had been associated with that guest on the source machine. And so we can, in fact, instantly reclaim those resources for other caching purposes, and there's no danger of any cache coherency problems if a guest happens to be bouncing back and forth between hosts. Another unique feature of our offering is role-based administration.
Before you move on, Rory,
Sure.
so the pre-warm is built into the default vMotion workflow?
Yes.
It applies to DRS as
Yes.
well?
So you're taking a look at the load imbalance metric? Actually,
So we are not controlling the vMotion event. I mean, typically the load and balance metric analysis is done to determine that you want to vMotion, right? So that decision's already been made. So we aren't in any way looking at that ourselves.
So are you delaying the vMotion to allow the pre-warm data to get there first? Or
No, we do not hold the
okay,
vMotion.
so you're racing.
Right. So that's one of the reasons why we pre-warm in rank order, so that the hottest of the hot is there without delaying the vMotion unnecessarily, right?
Okay, as opposed to vFlash, which is going to move the whole thing across the vMotion network.
Right. Okay.
And all of the data is moving via the shared storage.
Correct.
If it moves at all.
Right.
All right. So another unique feature is role-based administration, where you can specify access and control rights for our product to specific users. This allows control over various host-level cache settings as well as per virtual machine cache settings. In addition to this, we collect statistics and usage information for up to a month. I'm going to go a little bit quick here and say, what do people use that for in practice? Well, we have a number of customers that are actually cloud service providers, right? And what they use role-based administration for is self-serve admin. They're pushing cache control down to their customers. So essentially, they can now allow their customers to control the caching characteristics and set caching policy on the virtual machines that they're responsible for without being able to affect the operation of other virtual machines in the same shared environment, right? They can assign various rights to various customers, controlling who sees what, who can control what, and then those statistics that we've kept for the last month are the basis of a chargeback mechanism for these customers.